Okay, so I'm giving a short introduction to JuliaEO and MapCube and what you could do with that. So I think I'm not going to go into detail in the interest of time. Yes. Yes. Better? Okay. So as Raf said, that JuliaEO is basically a package building on dimensional data. So the idea is that this is for very large data sets that are much larger than your RAM. So everything lives on the disk or on some cloud storage. So you don't want to access the data if you don't necessarily need it. And then you want to process some data on it. And as Rafa said, we would like to, or I think it would be valuable to merge the raster functionality or the input functionality into rasters, and then only have the so-called MapCube function in JuliaEO that I'm going to talk about. So we start by loading some ZAR data. This is now a very, very small data set, just that it runs a bit faster. So we get the data as we would also get it in rasters or dimensional data with axes and some metadata, and then we can access it. And then we have the MapCube function, which is basically a generalization of a map slices, because in map slices you can only apply a function across one dimension. In MapCube you can combine multiple dimensions in the input but also in the output to do all kinds of analyses. And so the first one is to apply a simple simply a function across one dimension. You specify the input, you specify the outterms, which is empty because it's a reduction, and then you can apply this function. So, and then here we always, or you can pre-allocate the output to basically improve performance, because you then can reuse this this data for multiple parts of your chunks. And then if we apply the median over time, it takes 10 seconds, and you get a data cube that is reduced in one dimension. So you lose the time dimension because you reduced over it, and then you can continue working on that. And apparently I didn't restart the whole thing, which is bad. So we don't look at the map, but hopefully while I'm talking, this is also already doing the computations. So you can also map on all elements, or you could also use broadcast to, here in this example, to convert from Kelvin to Celsius. And then we can plot it. I think the stim array is not needed anymore. And then we can use this MapCube function to actually combine multiple dimensions. So here we define a norm. So we normalize the time series data by the mean and the standard deviation, but we want to keep the mean and standard deviation as extra variables. So we can here define, okay, we have not only one output, but we have multiple, and we have one input. And then we define the functionality, which is just normalizing by subtracting the mean and dividing by the standard deviation. And then in the indims and outdims, we define, okay, the input is the time axis, and the output is for the first one is the time axis, because it's just a normalized time series. and for the others, it's empty, but we write the data into a means.nc or a std.nc. And by doing that, we define this map cube where we start with the function, and then we can, I should still run it, right? Basically, it runs and it constructs all three outputs. And then we also can apply functions on moving windows, where you, for example, have a spatial, you want spatial averaging, or you want a temporal averaging, or some combinations. And here again, we define the inner function, which is apply to mean over the missing values. And then, yeah, this is the output of the, that's a strange output. That's the standard deviations of the air temperature. And then here we can apply this mean. And here in the moving window, we define as input moving windows, where we say, okay, the axis is the longitude, and then these 2x2 means take 2 pixels before and 2 pixels after your current pixel. So you could, for example, in time series analysis, you could say 1 or 0, so you don't use the future to predict the value of today. And so you can do skewed things, and then you basically apply I should make the figure, and so we have the averages, the means of the air temperature, but then we can also, and then we can compare this to the mean of the average filtered means, and we see this blurring effect. And then we can even define new output dimensions, which, for example, if you do temporal decompositions, you could say you can either apply a FFT, or you can we're going to use signal decomposition, where you can basically say, okay, my output is not a reduction, but actually I'm increasing the number of dimensions, because I'm splitting my time series into a trend component and a seasonality. And then apparently I broke something here. And so, yeah, this is just the time series of air temperature here in Angra. And now if we would do, now we can, so this would be just for a single time series, or for this one single point. We would have this, okay, we decompose this time series into some seasonality and some residual, and then we can apply this for the whole thing and here we define an extra output dimension where we define a dims. So we say, okay, as output we have the time axis, and we have a special scale axis, which we define new, which has 2 components, which is seasonal and anomalies. And then here we basically save the first output into the first part of the axis and the second output into the second. And this is just the inner function, and then we apply this by using the input and output dimensions. What did I do wrong? What? What? Decompose. Okay. Ah. Okay, apparently too many packages wanting to use the name decompose. So, are there any questions so far? Am I? So yeah, and now we see that we basically converted our 3-dimensional data cube to a 4-dimensional one by adding this scale dimension, and now we can actually plot it and see that the data is basically exactly this is the same as the one we did where we did it manually without using it on the cube. Yeah, I'm not going to plot these. And then another thing that might be quite useful is that you could use R or Python functionality if you have some legacy code so you have your Python analysis that works on a single pixel, but you want to scale it to larger areas. You can use Python call for that. So you could basically import your Python functionality and then use that in your inner function. And okay, Conda is taking quite long to load, but I mean here we just basically use this SciPy ND image Gaussian filtering approach, and then you only have to make sure that there's this PyConvert where you have to ensure that the type fits into the Yax array. And I'm going to just do it. And so this was all single threaded and on a single worker, but you can also use Yax arrays to quite easily upscale your computation by using distributed or using threads, and the Yax array package is going to use whatever resources you have available. So the idea is that here we just use distributed, we add some processes, but also if you would start Julia with multiple threads, it will also use them. And then with distributed, you have to make sure that your packages that you're going to use are loaded on all workers. And then you also have to define your inner function on all workers. So once that is done, and then we can also use it as we would normally, and that is, I think, taking some time because it's still has to compile some things. But if we do it again, it should be 2 seconds, right? So we see here this takes 2.5 seconds, while the first one took 18 seconds. So this is just speeding up your processes a bit. And that's everything I wanted to talk about for in JuliaEO. And I mean, yes, so we, as Rafa said, I think we should streamline the integration between JuliaEO and rasters a bit, because JuliaEO has some of these loading capabilities that could live in rasters, and I think the JuliaEO package focuses most on this mapcube functionality and on these automatic parallelization schemes. And now I'm just have a look at whether this is actually loading again. Okay. Apparently my internet connection here is too bad, or it's something broke in the last 20 minutes. Because I also wanted to talk a bit about Pyramid Scheme, which is a package for plotting large raster data. And the actual idea would be that, here we can now, this is now a leaflet map where we should be able to plot above ground biomass data on a 100-meter resolution, because the idea is that you have often in geospatial have data that is much larger than your RAM, but especially much larger than the pixels you have on your screen. And one way, and then you want to visualize them and you want to use them. And let me just try it once again. Or I can just show you the example in the documentation. Okay, now something broke. So the idea behind Leaflet is that you have this 100-meter resolution dataset, and then you can zoom in on the fly, which works by pre-computing these higher these coarser resolution data and only showing the data that is currently visible on your screen. So the idea is that, for example, so why would you use this? The one case is that you could do computations on these pyramids, but if you do a simple diff between two high-resolution data sets, it would take a few hours till this is computed, and then you can look at it and see whether there's something wrong in your analysis or whether there's some interesting patterns. And if you're using a pyramid, the idea is that you reduce this time that you wait till your data is done. This works by, as I said, we start with this high resolution data, and then we aggregate 2 by 2 pixel windows together until we are at a size that fits into your screen. And that's why it's basically it's a pyramid, because the data size gets smaller the higher up you are. That's basically like also map tiles in OpenStreetMap or Google Maps work. And then there's a way to compute this. So you can either use in-memory data, where you can just basically compute this on the fly. So in 30 arc seconds, this would take a minute, and then your data would be ready to be plotted and interactively played with. And then, or if you have larger data on disk that wouldn't fit into memory, you can pre-compute the different layers of the pyramid inside your ZAR folder, following the emerging standard that is currently used in the ZAR world for this, so that you can then later on use it, or use it also with other tools. We have access to pyramid data from different data types, like ZAR data and GeoTIFF. And I don't think that there's more pyramided data in geospatial that is relevant at the moment. You can access the data either locally or in the cloud, because this is basically just using the other functionality from the ecosystem underneath it. And you can then also do computations on the pyramid. So currently we implemented broadcast between 2 pyramids of the same size, so that you can do this. But in the future, I'd also like to implement broadcasts with scalars and all these other things, and maybe even tap into the functionalities of Discovery Engine. Yeah, and then yes.
So that broadcast is applying that operation on all layers of the pyramid.
This broadcast is basically applying this lazily on all levels of the pyramid. And then as soon as you do something with it, either save it or, most likely plot it, the function is applied on the data that you're currently looking at. And that's why it's much faster than having to... The alternative would be to do the computation on the whole data set and then try to plot the data that you're interested in. But this way you can basically just register your function and then apply it when you need it. That's the main idea, yeah. To just give a quick outlook. So we're also working on pyramids in multiple dimensions. So what kind of works is you have high resolution geospatial and a few time steps, so you can just build your pyramids in space and keep the time dimensions as is. But what I also would like to look into is do aggregations in time as well, because we also have the use case of rather coarse resolution spatial data, but 5-minute temporal resolution, which also blows up your memory and is not going to be able to plot. And we could look into understanding more formats. We could look at WMS, WMTS, and as I said, integrating Discovery Engine computations, so to open it up for more use cases. Yes? Yeah.
How do you expose existing pyramids to WMS?
So what works? but I can't show at the moment because it's broken. Hopefully I can fix it tomorrow, is exposing it as XYZ. So basically what you do is you set up a small tile server that then reads the data and then just gives out images. And then you could, I mean, we could try to do this also in WMS, WMTS, or you could, and what also works is the other way around. You load data from a map tile server and expose it as a pyramid.
Is that still the scope of this package? It's also sort of what Tyler has to do, right?
Yeah, there's some overlap that we should sort out in what functionality should live where. But we have a PR that kind of works to get a map tile as a pyramid.
So generating data so that it fits into this huge specific implementing a WTMS or WMS server, I would strongly advise against.
Yeah.
Just because you have to touch a whole load of XML to be compliant with some services.
Yeah, I mean, most likely this is just, I mean, yeah, maybe not. Maybe someone actually needs it, and then someone will come up with it. What?
Then he or she should pay us to do that.
Yeah.
Probably not. But for WMS, I'm okay with that.
Yeah.
Have you benchmarked against GDAL? I was thinking, you know, like you can generate the pyramids for a geotiff or something like that, just to see if there's any difference in performance.
Not yet, but yeah. It's on the roadmap. I mean, it's on the issue list to benchmark against JuliaEO to see whether there's some what's the overlap or what's the performance. Yeah. Okay. I'm done.